in class we didn't have time to make it through this example, and I think this is something you might need for finishing the homework. So I wanted to give you a little bit of information on how we do a matched pairs problem from the beginning to the end. So this example is about the comprehensive assessment of outcomes in statistics. It's an exam and is an online multiple choice test on concepts covered in a typical introductory statistics course. Students take one version before the start of the course and another version after the end of the course. So you can see how this is matched pairs because it would be the same student doing a before and an after. So before and after scores for a possible random sample of 10 students are shown below. So we have students A through J, they have the before scores and the after scores. So remember this being a matched pair design, what we really are interested in is the difference in their scores. So if we were to find the difference here, so this is where we want the difference. So 43 to 60 is a gain of 17, because remember we're looking at after minus before, so we're really looking at this one minus that one. So 60 minus 43 is 17. 45 minus 40 is 5. 55 minus 48 is 7. 80 minus 65 is 15. 85 minus 60, that's even bigger, 25. 71 minus 48, that's 23. 52 minus 43 is 9. 35 minus 38, oh, this one's minus, so that one lowered their score by 3. 54 up from 43 by 11 points, and 55 minus 55 will give us 0. So notice we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 differences. So we are interested in determining whether taking the course increases students' understanding as measured by this test. So why should we do a paired design rather than two separate groups? Because we're really looking for the difference in the same student after they take the course and before to show the effectiveness of the course. So we're really interested in the increase in scores for each individual student, and pairing the data reduces any random variation and other possible confounding variables. So I'm not going to write all of that out because you have that in the course packet solutions that are posted on Blackboard. Part B says define those differences for our 10 students, which we did. And it says state the mean, standard deviation, and sample size for the differences here. And this is where things get interesting because now you have to go to StatKey. You put in your 10 differences as your data, and then you ask StatKey to tell you the mean and the standard deviation, right? So we know our sample size. Our sample size, N, here is 10. But we need to go put all this data into StatKey under one quantitative variable and come back with the answers. So here we are going to StatKey and under one quantitative variable. And then what we need to do in our one quantitative variable is edit our data. We need to select all the data that's there, delete it, turn off the checkboxes, and then go back in and enter our data for each of our differences in our matched pair data. So 17, 5, 7, 15, 25, 23, 9, -3, 11, and 0. And then we can close our window. And when we go up to the right, we see that we've got our sample size is 10, our mean is 10.9, and our standard deviation is 9.219. And we can use all of this information to finish this problem. If we copy in the rest of the information from StatKey, we have our X bar here. And remember that this is with a subscript of D. Oops, so is our sample size, because these are for matched pairs. So it's a paired difference in means. So paired difference in means. So our X bar D was 10.9 from StatKey, And our standard deviation for our sample that A is matched pairs was 9.219. So we need to define the differences and then state the mean, standard deviation, and sample size for all of them here. Then part C says test to see if the scores at the end of the course are higher on average than scores at the beginning of the course. We want to show all details of the test, including hypotheses, checking our conditions, calculating our test statistics, a sketch, naming the model, that means normal or t, our p-value, our conclusion, and our interpretation. So that's a lot. So I'm going to put a little bit of these, a little bit of the calculation information above here in part B. So we know we're going to need a standard error. So let's find our standard error, which is going to be S sub d, our sample standard deviation, divided by the square root of n sub d, or our 9.219 divided by the square root of 10. And when we calculate this, we get 2.915. So a few more things that we're going to have to do now is we're going to have to define our hypothesis test. So we need to define our null and alternative hypotheses. We also need to state our sample statistic, and we need to state our test statistic. So let's take this one step at a time. Let's define our parameter of interest, mu sub d. So mu sub d is going to represent the mean increase, right? The mean increase on a student's score after taking an intro stats class, an introductory statistics course. And so we need to state now our null would be that the mean difference would be 0. So our null is that it doesn't make any difference in their score on the test. Whereas our alternative will relate to our sample mean, which was positive. So we'll say that we think the true population parameter, the true population mean, is also positive. So we'll say it is greater than 0. So let's find our test statistic t. So t, remember, is our sample stat minus the null over the standard error. So here we would end up with our 10.9 minus our null is 0 over our standard error, which we got was 2.915. If we do this, we find out that our t-value is 3.74. So if we were to go back to StatKey and do a right tail test, so from here, we're going to go to StatKey, and we're going to go to a theoretical t, right? Theoretical t distribution, because this is a matched pair mean. So go to the theoretical t distribution, and our degrees of freedom is going to be n minus 1, so it's going to be 9. And then we'll use a right tail test, and we'll plug in our t equals, so for t equals 3.74. And when we do that, we get a p-value equal to 0.0023. So with this in mind, our p-value is now less than alpha, right? So no matter what alpha is, this is a really tiny p-value. So we're going to say our p-value is less than alpha, so therefore we will reject the null. So we have convincing evidence, we have convincing evidence that on average, scores increased after taking an intro stats class. And then part D asked us, what is the average increase on the exam after taking the course? Compute and interpret a 95% confidence interval for the improvement in mean CAOS scores between the before and after scores. So here, what we're looking for, and if you go back to your formula sheet, you'll see this on there. We are looking for a 95% confidence interval. So here, that means we are looking for our sample stat plus or minus T star times our standard error. And remember, our standard error is 2.915. Our degrees of freedom is 9. So we can go find T star. Our X bar D we know is 10.9 plus or minus, and we find our T star on our theoretical T distribution using a 95% two-tail test. We find that our T star is 2.262. And again, if you don't get this number, make sure you've edited your degrees of freedom from a previous problem. So we end up with 10.9 plus or minus 2.262 times our 2.915, our standard error from before. And that means that we end up with 10.9 plus or minus 6.59, which leads us to 4.31 to 17.49. And if we interpret it in context, we are 95% confident or sure, we're 95% confident that the mean increase in scores on the, I kind of want to call it the chaos exam, the CAOS exam, and I know chaos has an H in it. So the CAOS exam, after taking an intro stats class, is between the two numbers we got, 4.31 points and 17.49 points. So this should help you be able to do the section 6.5 homework. And I'm sorry that we didn't get a chance to get to this example today.